shape of speed and dimensions of the jet, size and shape of the bottle, or water temperature to affect the sound. So nevertheless, let's get into the relevant parameters. First relevant parameter is the volume area of the bottle. Then I'll investigate jet diameter, jet height, and the temperature of the water. So an overview of my presentation. I'll first go over the reproduction of the phenomenon. Next, I'll go on to my experimental setup and my measurement techniques. Next, I'll show you my theoretical model. And next, I'll go on to my key parameter interactions. And finally, I'll conclude my presentation. Okay, so first, I have a video of the phenomenon where you guys can see. So just a quick qualitative explanation. We can see that in our Helmholtz resonance here, as the bottle fills up, the frequency produced, you can qualitatively hear it increase. And this is because of the wavelength of vibrating air columns inside the bottle shortening, leading to a higher frequency. And along with the increasing average pitch, we can also hear the sound of bubbles and turbulence in the water. Onto my experimental setup. So we can see that I have, for my experimental setup, I have a bottle. And in the bottle, I attach quarter-inch tubing to the bottom of the bottle and fed it into a 12-volt pump. The pump was hooked up to a variable power supply, which then fed the water back into a nozzle, which fed it back into the bottle. And this was so I can keep the water level in my bottle constant as I did my experiment. I also have a thermocouple just in my bottle and in my water source just to keep the temperature. Looking at my experimental setup, I placed entire experimental setup inside a box, which was then surrounded by soundproofing material. We can see my bottle, which was 3D printed with various dimensions in mind, the nozzle, and my 12-volt DC pump. So how I measured the frequency and the peaks of my data was I used Audacity, and then I used I split the spectrum using discrete Fourier transform automatically. My first experimental measure is the nozzle flow rate. So we can see I can measure the surface area of my jet, or my cross-sectional area of my jet, or the jet nozzle. Next, I can calculate the amount of volume it takes in a certain amount of time, and I can apply the volumetric flow rate equation to get various flow rates for different voltages from my power supply. Next, on to my theoretical model. The first theoretical model I have to explain this phenomenon is Helmholtz resonance. So if we look at our bottle, we have our jet and our bottle. We can label the volume of air inside the bottle V. The length of the bottleneck can be denoted as L. The radius of the bottleneck is denoted by R. The initial radius of the jet is denoted by R naught. And the height of the jet to the water surface is H. So first of all, we can see that there's a continuous flow rate in the nozzle. And as the water falls, it accelerates. And using constant flow rate, we can determine the velocity of the water farther down from the nozzle, and that's we can obtain a different value for the cross-sectional area as you go down the jet. Now, onto Helmholtz resonance. The general formula for the fundamental frequency of Helmholtz resonance is equal to the velocity of sound over 2 pi times the square root of the area times over the volume of air in the system times the length of the net. The area is equals to pi r squared minus the cross-sectional area of the water jet, and we can now obtain this a general equation. And we can also see that the volume of air inside the container is proportional to 1 over the frequency squared. Plotting the experiment for this, we can see that we have a pretty good fit for Helmholtz resonance for the peak resonance frequencies inside a bottle. On to temperature and how this affects the phenomenon. We can see that the speed of sound differs in different temperatures areas. So we can model this by just studying in this formula here. And when we plot this, we can see that there is a general change in frequency. However, this change is very, very small over, let's say, 15 degrees. We can see that the frequency only shifts about 5-6 hertz. On to my next theoretical model, I have jet breakup. So, if we look at my jet, we can label the diameter of my jet as d, the length critical as the critical break up before, the length of the jet before it breaks up into droplets. V is the velocity of the jet leaving the nozzle. Rho is the density of the water, gamma is the surface tension of the water, and d is the diameter of each tiny droplet, which is different from the diameter of the jet. Okay, so on to the Rayleigh pathway instability. So we can notice that if we look at our jet, we can see that after a certain length, our jet will usually break up into droplets. This length can be obtained by or approximated by using this expression right here, which takes in these parameters, and you can calculate the length of the jet breakup. Also, we can see the effects of temperature on this. We can see that as temperature, this is just empirical graph from literature. We can see that as temperature increases, the surface tension of water also usually decreases. And also we can then plot the jet breakup length versus temperature. This is also theoretical. And we can see that at higher temperatures, the jet takes a longer distance to break up into small droplets. So onto our droplet size. We can see that after a length, a critical length has been reached. First, we can look at our jet, and we can notice that there are surface waves on our jet due to the Rayleigh pattern instability. We can also see that from literature, we can obtain that the optimum wavelength of these surface waves is equal to 4.51 times the diameter of our jet. For our droplets, we can then convert the wavelength, assuming it's a cylinder, and we can approximate the diameter of each water droplet, which is approximately 1.89 or 1.9 times the diameter of the jet. So each droplet is slightly larger than the actual diameter of the jet. Next, going on, we can look at the dimensions of our bubble. We can note omega d as our droplet volume and omega sub b as our bubble volume. Looking at how bubbles are produced when droplets hit the water surface, we can see this function here, where omega b and omega d are the volumes of the droplets in the bubbles, and SG stands for the Stokes number to the power of -4/3, and they have this relationship right here. This is a pin from literature again. For the volume ratio to temperature, we can see another theoretical curve, and we can see that as temperature increases, the volume of each bubble should increase. The limitations of this theory, we can see that the equation above cannot predict the actual distribution of air bubbles resulting from the actual jet hitting the water. It only applies to single droplets hitting the water. And so if you have a jet, we have to have a different theory. So on to our last theoretical model, linear resonance, which is the resonance of air bubbles inside our resonator, or our bottle. On to the geometry to denote the radius of the bubble at R. And we can see that the formula for a spherical bubble, which is approximately most of our bubble size is 1 over 2 pi r times 3 gamma times the pressure, ambient pressure over the density of the square root. And we can see that once we evaluate this for our constant, we get approximately 3.26 over the radius of our bubble in meters is the frequency produced by each bubble. And obtaining our bubble size. So of course, I tried many ways to obtain the bubble size for our experiment, but in the end, I just decided to empirically count them all. So in order to determine the distribution of the bubbles in my experiment, I devised a new experimental setup where I replaced the bottle with a transparent container, put in a ruler, and I obtained the bubble size of each bubble using tracker, and I gained a distribution. After getting this distribution, we can plot the peaks or the higher bubble counts into a spreadsheet, and we can also see the bubble height with ratio. We can see that they're mainly spherical. As for experimental verification, we can then plot the peaks that we get from linear resonance and Helmholtz resonance. Okay, and when we plot the peaks of each one, we can see that they match up pretty nicely. As for experimental verification, we can then plot the experimental peaks versus our theoretical peaks, and we can see that they match up almost perfectly 1-to-1. There's a couple offsets and they don't match up perfectly, but that's expected. As a sort of parameters, we can see that by varying temperature, we can see our resonance frequency of the almost resonance would gradually increase slightly over time. The volume ratio of bubbles to temperature, the volume of each bubble will increase as we increase the temperature of the water. And varying the volume of air, we can see that the Helmholtz resonance peaks also match up with our theory quite well. In conclusion, when a vertical water jet, in conclusion, we started with first determining the breakup length of our jet, which will then contribute to the amount of the distributions of our droplets. If we move our jet higher up, we'll see more droplets. If we move it lower down, we'll see less droplets. And then we also explored the theory of Helmholtz resonance. And after using everything into account, we can generate a theory of all the peaks or the peak frequencies in our spectrum. We can see that they line up quite well. Here are my references. Thank you for listening.
Okay, thank you. So it's time for questions from the audience. So firstly, I would like to ask you, why do we need a bottle for this particular phenomenon to observe?
Why do we need a bottle?
Yes. Because why is there a bottle? I don't see it from your presentation.
There is a bottle.
Yes, it is.
Oh,
why?
Why is it? Because the problem name is filling up a bottle. It's in the problem.
Okay, I don't think this is a satisfactory. Yeah, so we can move on. How precisely does the jet breakup affect the properties of sound?
Can you repeat that? How
the jet breaking up? Yeah. How does it affect the properties of sound?
Oh, okay. So usually, the jet breakup affects the number of bubbles. As you have more bubbles, you will hear more turbulent sounds in the water. If there are no bubbles observed, you will not hear much turbulence at all.
Thank you. Among properties of sound, there is the amplitude of sound.
Yes.
Were you investigating this?
No.
Okay, thank you. Were you investigating the bottle shape as the task encourages us?
Yes, I changed.
Okay. Okay, we will look into that in the discussion. So what is then the meaning of the neck length? What effect does it have?
It varies for it changes the peak frequency for Helmholtz resonance.
Can you qualitatively tell us?
Oh, qualitative. It's so when you have a drinking bottle, it's just
with wider neck. With wider neck.
With wider neck, you have a greater cross-sectional area.
And how does it affect the properties?
A longer neck will have a lower frequency, and a greater cross-sectional area will also have. If you look at my Helmholtz resonance, we'll also have a higher frequency.
Okay, thank you.
Okay,
3 minutes time for preparation. Good morning. Okay, so check that. You'll have an extra 10 seconds because the projector is off. So we'll just make sure they're not working in the slides anymore, and we'll wait for the projector to turn on for this device for everything else. Because, I mean, it's not their fault. Okay, I guess so what? We'll have Clark for the opposition. Good morning, ladies and gentlemen. My name is Kevin, and I'm going to oppose the task number 5. Firstly, we will read the problem statement. We are to look into this effect, in which we are to investigate the relevant parameters, such as the dimension of the jet, the size, and the shape of the bottle, with water temperature affecting the stats. In the report, we have seen the phenomenon demonstration, some of quality
Yeah,
Sorry,
it's on
like
discussion.
the clock messed up and now the time is running for the discussion.
You have 14 minutes.
Can you go back to this previous? Can you stop the clock?
We just had the 4 minutes for the opposition, right?
Yes.
Yeah. So right there, and now we set this to 25 seconds, please.
I can start from the beginning if you will.
Okay, let's start from the beginning. Can you reset it?
Yes.
Okay, 4 minutes for the opposition.
Okay, good morning, ladies and gentlemen. My name is Eric and I'm going to oppose the task number 5. In the statement, we are encouraged to investigate relevant parameters such as are the dimensions of the jet, size of the jet, shape of the bottle, and the temperature of the water. In the report summary, we have seen the phenomenon demonstrated. We have seen qualitative explanation or attempt for qualitative explanation, but we really lack in this part. Among the quantitative explanation, we have seen the Helmholtz resonator as the main effect affecting the temperature, affecting the properties of the sound. So, as for the apparatus, we really liked that you were using the damping box to filter the background noise. So for the theoretical model, we were using the Helmholtz resonance. But with Helmholtz resonance, it is known that it sometimes the bottle neck acts as though it were larger, as it indeed is. And this requires some end correction, which we have not seen in your theoretical model. Also, you are investigating the source of the sound, the bubbles, but you are investigating them only in the bottle itself, and we would like to see how it compares with when looked at this without the bottle to compare the effects. Because the formulas we were using were, well, without the bottles. You were filling up your bottles, but we have not seen the tendency of the sound and its frequency on the time. Also, the task encourages us to study the sound, part of which is the amplitude. We have not seen this in your report. You were investigating a lot of time the jet breakup, but we don't see why it is important. And with this, in your qualitative explanation, we really lacked why do we need even the bottle. We think it is due to, it picks up some resonant frequencies from the sound, but we would like to see this stated. Also, there is another phenomenon which lacked in your presentation, and that may be this deformation of standing waves. Also, you were encouraged by the problem statement to investigate the relevant parameters, such as was the neck length, the bottle, the size, and its shape, which we also lacked, and I would like to see if you have it in the discussion further. Also, the jet velocity was not thoroughly investigated as we would like to see it. From our suggestions, maybe that to pick up all the phenomena, such as standing waves you clearly missed, you could use, for instance, spectrograms of the sound to show us if there are, for instance, these. Moreover, in our theoretical model of the Helmholtz resonance, for instance, we have seen that you are using speed of sound, which is affected by the temperature, and we did not see this effect discussed in your presentation. So these are points also for the discussion, and I think we can move on to it. Okay. So shall we?
Yeah, before we start, can I just like clarify a couple things?
Yes.
Okay, yeah. So you said I didn't have an NP correction on Helmholtz resonance. When I did my experiment and I analyzed the data, I saw that the peaks just matched up immediately, and so therefore I can conclude that N corrections are not as relevant because otherwise my data would match up.
That is understandable, but we would like to see at least some discussion because this is a known effect. Yeah, so why precisely weren't you investigating how the sound changes with time?
Oh, okay. So what I did instead is, so you can see how as the bottle fills up, the water level changes. My experimental setup allows for like kind of just a freeze into one moment of time where we have a certain water height, and so we can just change the water height.
But what we really see with sound are dependencies on the time, because we can see, well, there is frequency and it is time dependent, and so we would like to see more of this. So let us move on to your theoretical model. So please could you turn on these slides? So you say that temperature affects the phenomenon because it affects the height where the jet breaks. But I believe that also, could you please turn on the slide with the Helmholtz resonator formula? I believe that there is a speed of sound in the formula. Maybe if you go even in the original Helmholtz formula. And yeah, this is affected by the temperature. Did you discuss how that?
Sorry.
Well, the speed of sound is affected by the temperature.
Yeah, it is.
Yeah, and
the speed of sound is 31.4 approximately plus 0.6.
Okay, I see.
Yeah, and then I go to the next slide. I plotted this out.
Okay, I see. Okay, with this I see. So is the dominant effect here the jet breaking up, or is it that this depends?
I believe the jet breakup is more relevant than the shift in frequency.
Okay, but is it accounted for in this particular graph?
Yeah, it is.
Okay.
This is just a peak Helmholtz frequency.
Okay, so it is peak Helmholtz frequency, but,
Yeah.
But I don't see how the jet breaking up really affects the sound. So could you elaborate on this?
So as the jet breaks up into droplets, they'll change the properties of the bubbles. For example, if the bubbles, if the drops have higher velocity, for example, you'll have a greater ratio between droplet size and bubble size, as we saw in the relationship to the Stokes number. And so it will affect mainly the bubble surface, which affects linear resonance more than.
Okay, and so qualitatively, can you say how? With greater bubbles.
Yeah, so with bigger bubbles, you will have a lower frequency produced. With larger bubbles, yeah, you'll have a lower frequency produced.
Okay. I believe that the number of bubbles should mainly Well, the bubble formation should mainly affect the amplitude of the sound, but I can see from the theoretical model that you are getting for something different. So let us move next to the bottle shape. How does this affect the bottle?
Can I just say something about amplitude?
Yeah.
So I did notice that in literature I read that amplitude is approximated as the radius of the bubble power 3/2 times u, which is the inward normal boundary velocity of the bubble. The problem I had with this equation is I couldn't necessarily find the right piece for u, but I can say that as the radius of the bubble will increase, you will have a higher amplitude, qualitatively. That's all.
Okay. And here, I can agree with this, but here, why does it not use, why is the dimension of this different from this?
Sorry, this top part has units. They're just not in it.
What are you? So what precisely is this quantity?
It's just calculated from my Helmholtz equation right there. You would simplify the things for standard
Okay,
deviations.
we would like to see this stated in the presentation.
Sorry, yeah. It's approximated to 3.626 with the units in. It's just not, yeah, written in.
Okay, and we also believe that the amplitude is mainly affected by the number of bubbles. So your Helmholtz resonator, it predicts one frequency, but what about the others? And that can be formed by the standing half waves in your resonator.
Could I ask you to use a different color, please, because it's really visible. Thank you. Thank you.
Thank you. Like there can form these half waves in your resonator.
Sorry, like, where? Like, can you draw a bottle and?
Yeah, this is the bottle, and
Yeah.
there is a sound produced here. And now there are, I think that there is also a formula that can predict the half waves that would form like here as such. That predicts the frequencies that should be also picked by your resonator.
Yes, if you look at my my peaks, it could very well be one of the uncounted peaks in my.
Well, but Helmholtz resonator does not include these.
Yeah, it does not. It could be one of the smaller peaks that are less relevant.
Okay, but you show these smaller peaks, and clearly they are larger than the ones that are here, rather randomly distributed. But
These are just
okay.
based on
And you were not investigating on such peaks while you were focusing on these. I believe this is a mishap.
Yeah, so first of all, there's a lot of noise in my experiment. It's very difficult to cancel all of the background noise off. I did do subtraction on this from ambient sound. However, it wasn't as effective. First things first, I would just like to clarify the bubbles. How I calculated the frequencies of the bubbles is I kind of went and took a distribution of the bubbles. And for each distribution, I put it into a histogram and average values. And that's why you see just a main peak, but there's also many frequencies go down.
Thank you. That's understandable. Could you please leave that slide on? Because I would like to clarify one more thing. We have seen many peaks here predicted by the Helmholtz resonator. But from the Helmholtz resonator, we should see only one peak because it predicts only one frequency.
No, it predicts a fundamental frequency and there's higher frequencies. I've noticed that in my experiment, you can clearly see multiples of that frequency in like exact frequencies.
Okay.
Multiples of that frequency.
Okay, so this should be also
Like
this should be also clarified in your presentation because the Helmholtz resonator should pick one frequency. Well, really, and are these really multiples?
yeah, these are exactly multiples of the first fundamental frequency. And you can see each of them. And so I could only explain this with higher harmonics of Helmholtz resonance. That's the only thing I could think of. And it does match up.
Okay. Speaking. you stated in the beginning of our question that you were indeed investigating with the bottle shape. Could you show us
Yeah, so
this?
originally in my experiment, I started with just to explore Helmholtz resonance. I started with an ideal Helmholtz resonator. As you can see here, this is just the ideal round,
Yeah.
perfectly spherical one. Then after to make sure that it matches up, I elongated the bottle into different
Okay,
angles.
were you investigating such as wider necks? Because we believe Helmholtz resonance is not applicable to wider necks, and it is, well, among the statement of the task to investigate different voltage geometries, wider necks.
I did not.
Okay, thank you. Okay. I believe that we have cleared many points in our discussion. Yeah. There are some discrepancies with the theory of Canadian peak, as we have seen, among which is, the fact that they were using the Helmholtz resonator, although it is not applicable for, voltage geometries. Also, we have seen that they were not investigating some phenomena that could occur, such as RT stable standing half waves. And also they were not investigating the amplitude of the sound at all, as we found later in the discussion. That they did not. Yeah.
Okay, I'm afraid there's no more time for additional remarks, and there'll be 3 minutes time for the reviewing team to ask questions.
Good morning, my name is Nika Grigo, I'm a member of Team Rush, and I have questions for the opponent and for the opponent. So firstly, what will change if you haven't got a neck of the bottle? So we have a cylinder. Something will change and your...
Like no neck at all. Like just round glass, for example.
So we will have only a cylinder.
Oh.
Will we absorb this effort?
You'll
And,
see standing waves instead of Helmholtz resonance.
and your opinion?
We believe that with cylinder, the Helmholtz is not applicable, and we would need theory for quarter waves.
Okay.
Standing waves, yeah.
Okay, thank you. And what about the linear resonance? Will the frequency changes as the bottle filled up?
As the bottle fills up, as long as the size of the bubbles are constant, it will. But as the bottle fills up, the bubble properties will change as well. So yes, you'll see a difference in linear resonance.
Okay, thank you. And what is your opinion?
Could you please state the
The linear frequency changes on time? As the
well,
bottle filled up?
Yes, the dominant frequency indeed changes with.
Okay. Have you changed the volume of the bottle?
Yes.
And can you open the 36 frame? Okay. And when you opening this, can you answer the question? How the number of bubbles will change their observant effect?
How the number of bubbles
Will
the
change
number,
the number of bubbles.
I'll change
in
the amplitude.
What?
The amplitude, the loudness of it. As long as they have the same radius and dimension, the more bubbles you have, the louder it'll be.
Okay. Thank you. And how did you measure this peak? So, what is the criteria of this green and blue lines? How did you find it? Because I see some peaks and you find not the largest one. For example, the last in the frame.
Okay, so the green ones are Helmholtz resonance taken from the dimensions of my bottle, theoretically, and the blue ones were based off counted distributions that were determined empirically by counting bubbles in my camera setup.
Okay, thank you. And in the solution of the problem, we see that have you changed the diameter of the jet?
The diameter of the jet?
Yeah.
I did, but it's not in my presentation.
The speed of the jet?
Yes, I varied voltage.
Okay, and the size of the jet and the size and shape of the bottle?
I changed bottle dimensions.
Okay, and not the shape, maybe they are this one or this one.
For the bottles, I mainly kept them round, yeah. But like they were elongated.
Okay, and the 18th frame, if I 18th frame, please.
8.
Well, how can you, is it a linear dependence or not?
Okay, I'm sorry, there will be
Okay.
no more time for an answer, and you gotta proceed to operations. Okay, could you please stop the clock for the review?
So, good morning, my name is Nika Vigo, I'm a member of Team Russia, and today I'm the opponent of the I'm the review of the problem number 5 in the border, so everyone knows the statement was a problem, so let's find the main results of the records. We can see that there was explained the reasons of sound change, but not the why the sound appears, so there wasn't importantly the reason of appearance of the sound, so there were some frequencies change in the time of tense, that there was a hand-hold resonator as the reason why we can see the amplifying frequency. Also we can see the jet breakup which we were taking into account, but there was no reason why relay proton stability is really important. There wasn't a reason of why it is really important in this phenomena. So also we considered the minaret resonance, and we can see that it is a resonance to the bubbles, and then was the graph which shows us the diameter distribution, and we understand that in this problem it is one of the important places, but not the main point of the record. So also we can understand that there were some strong points of the records. Firstly, there were two resonators we observed, and we understand that it is a good part of the problem. Also, there were a break in jet into the drops taken into account. It is a relay plateau instability. It shows us why we can hear the sound, but it wasn't said that it is the main reason why the sound appearance. Also, there were experimental setup with the sound isolation. So we understand that absorber panel planes are very important in this question, because there wasn't the different sounds from the room, for example, or for the place where we can conduct the experiment. But there were some points which we can't develop in this record. Firstly, there was no reasons of sound appearance at all. We can see that there is a sound, but there is no the reasons of appearance. No explanation why different peaks are predicted by the model of reasoning. No neck row. Also, there were poor frequency investigation, because it is the main problem, but it wasn't done. And also, we are not fixed microphone in the observation, as we can see, and it is not really good, because we have a different sound from the different angle. So when task fulfillment, we understand that it's not so okay. We see that the sounds may be produced. We saw that. We see that the proper frequency, so the sound may change. It was fully done, we see that they changes, but not understand why. We can see the investigation of the problem. Not all of them were found because we can see that the speed wasn't found, the reason why we use the speed wasn't set. The dimensions of the jet was not fully because we can, the size wasn't fully because we see not all parameters of the bottle that were changed. The shape of the bottle, why it's not a conus or the sphere not observed, and the temperature effect was done, and it's really good. So the problem was partially solved. What about the discussion? We can see, what about the opponents? We can see that there were a good point were noticed is the sound damping box, chemicals resonated, jet breakup, and wasn't reported, frequency was in time wasn't investigated, and the neck bottle size and jet investigation wasn't in the record. And so what about the missed points? We didn't see the reasons of the sound appearance, so why it is working like this. So we don't see about why the minute resonator works, so it wasn't mentioned in the opposing. So there was no said about the shape investigation, but it is one of the relevant parameters. What about the discussion? We can see that there were some good questions which can improve the physics in this reference. First, how the sound changes in time. It is one of the main problems, one of the main questions of the problem. So we agreed with. We understand that it's one of the points. So how the temperature effects? We think that it is a sound and surface tension. So what about why more than one
Okay,
frequency?
sorry to interrupt here.
Okay.
And there'll be 2 minutes time for the concluding remarks.
Okay, so first I'd like to address a few points made. So our nozzle has a constant flow rate. So basically, if you look at the volume versus frequency, it's identical to volume versus time in essence, because we have a constant flow rate, so volume is changing constantly with time, so you can just replace volume with a time step or a time vacuum. Next, they said they were talking about our experimental setup. How it worked is, in order to verify the Helmholtz resonance model, we started with an ideal Helmholtz resonator, which was a perfect sphere that we 3D printed. Next, we started elongating the bottles, and once we analyzed the data, we saw there was no difference at all, actually. And so we could accept this model of Helmholtz resonance. Next, lastly, the most important point I think they got wrong is they said that the jets, the Rayleigh plateau instability isn't really relevant. One of the biggest parts of this problem is jet surface interactions, how the jet breaks up with the water surface. Sometimes you'll see the jet breaking up and producing many bubbles, and sometimes if you hold the bubble really close to the bottle really close to stream, you will not see many bubbles form at all. You can qualitatively see that if there are many bubbles, you will have a lot of sound. If there are no bubbles, you will not notice the bubbles at all, actually. And the bubbles provide a very, very significant role in this. And by analyzing the drop breakup and the length, and taking this factor into account, we investigated more about the jet surface interactions, which is a very, very important aspect of this problem in my opinion. Thank you.
Okay, thank you. And there'll be 5 minutes time for 3 questions. Yes, please.
First, to the reporter, you mentioned that the main effect is the jet surface interaction. Could you please point out some main parameter which is missing maybe in your theory, but it affects mainly the formation of bubbles at the surface?
Okay, so if we go
Could you mention just one property of fluid which is important, but you miss it for simplicity? Could you mention? Because you have surface tension. What else?
the height that the water falls down.
Okay.
So if you
What the zone for flow is laminar or turbulent, we believe.
Okay.
The parameters of Rayleigh plateau instability.
Okay. Thanks.
Okay, one more question to the reporter. Could you bring up slide number 36 once again, please? Yeah, yeah. So, judging the green peaks, I see a very first peak at, let's say, 200 hertz, right? And the third peak at 1000 hertz. Are you sure those are multiples?
Yes.
Okay, thank you. No, thank you. Additional questions? Okay, if not, I get a question for the reviewing team. You mentioned in the reviewer's presentation that the jack breaker was the main reason why you hear the sound, right?
Yeah, because we understand that we will have a droplet, and we understand that if we will have a laminar flow, we won't see the sound. If we will have a droplets which goes to the surface, we will have a sound, and if we will have a turbulent jet with a high speed, we will observe the sound too. So the issues which related to the radial stability when there's the parameters of the jet, it is one of the important issues of the
Please, may I ask the opponent for a comment on that? Whether the jack breakup is the main reason why we hear the sound?
We believe that with turbulent flow, that there are already bubbles in it. Also, there is a gadget on the pipe that produces the bubbles, and the number of bubbles is the main reason for the formation of sound. Boiling bubbles.
Well, the reviewer insisted that there was no analysis for the frequency change with time.
Yeah.
So what do you mean by that? So it's not correct that in my point of view, the reporter used some kind of reparametrization using this flow rate. So it can recalculate the flow rate by the time. So you not agree with that?
I think that in this case, the main dependency is frequency and time, and we need to observe it because we can see how the frequency amplifies with time.
We cannot use the reparametrization
We can
time.
use, yeah, we
We
can use.
can recalculate, or we can't. In
We
principle.
can calculate.
We can't recalculate the time through the.
But we don't see the amplifying frequencies which are shown for everybody. So it's like a good qualitative explanation why we can see the effect. The dependence frequency on time.
Okay, question for the reporter. Can you predict the sound of non-spherical bubbles?
Sorry?
Can you predict the sound that non-spherical bubbles would emit?
Non-spherical?
Yeah.
Yes, like as long as they are elongated and round. I'm not sure about if you have crazy geometry with edges in them, but for any normal shaped bottle that you would see, we can predict the sound.
No more questions from Judy, I guess? Okay, then we'll move on to grading. And so yesterday we did it like this, that while we were compiling our mocks, the teams basically swap tables, so we have the same time during the break. So if you want to do so, you can do that like this.
So they use the second screen.
Okay, so if you're ready to go on, once you're finished moving, okay. So if everybody's ready, we can start showing our marks. First, for the reporter, please. I read out the marks from my side. It's 5, 6, 7, 5, and 5. For the opponent, please. That's quite uniform. Number 1. It's 7, 6, 4, 7, and 6. And last, for the reviewer, please. It's 5, 5, 4, 6, and 6. So there will be some justification needed.